Hello and welcome to episode 11 of Plants to Plants Hemp Processing Seminars by SciPhy Systems. SciPhy Systems brings industrial extraction and processing technology into the future, and Plants to Plants brings top-tier experts to the table to inform viewers about what it takes to go from concept to completion on a hemp processing plant. Before we begin, I ask anyone to call out any technical issues that arise during the session, and I also would like to direct everyone to the Q&A module on their screen if they hover their mouse over the window. Using that Q&A module, you can ask any questions that you have throughout the session, and we may answer them during the session if they're applicable to the topic at hand, or at the end where we will have a dedicated Q&A section. So please, questions are absolutely encouraged, and feel free to be communicative. Our episode today is X-spiral membranes, changing the game for solvent recovery with Zev Feinstein of Molecular Forces Consulting. Molecular Forces and SciPhy Systems have teamed up to bring new plug-and-play solvent recovery solutions to the market with never-before-seen cost efficiency. Membranes are breaking the mold, cranking up throughput while keeping a tiny footprint and crushing down energy expenditures in the process. In this episode, we review the remarkable benefits of this newly applied technology with the Molecular Forces founder, Zev Feinstein. Our guest today is Zev Feinstein. Zev is the founder of Molecular Forces Consulting, an MS in polymer chemistry with 5 years of experience in the hemp and cannabis industry. He has a special focus in extraction equipment design and the intersection between polymers and extraction. Recently, MFC has released the X-spiral line of polymeric membrane filtration systems for low-energy, room temperature winterization and solvent recovery, which we will be looking at today. To place this episode in time, so to speak, SciPhy Systems is currently in the process of multiple product development projects that we will be rolling out in the next weeks and months. We've been extremely excited to have Zev and the X-spiral integrate into some of those plans. If you would like to learn more about our new approaches, many of which are not public yet, you can do so by contacting us on our website or through email or on social media, where we can provide more information. If you would like to get in touch with Zev, please visit molecularforcesllc.com. That is molecularforcesllc.com. Today's episode, as always, is hosted by the SciPhy Systems CEO, Emmett McGregor. So without further introductions, I am going to bring up our guest and our host, and we can begin the session.
Hello.
Hello, welcome Zev. Great to have you on today, and welcome to all of our viewers. Thanks for joining us today. We see that folks are still trickling in, so thank you so much everyone for joining us. And this is really a thrilling episode. It's one we've been building up to for a while, where we really think that membranes bring a ton of advantages to the table, and especially these X-spiral membrane systems are an excellent platform both for cost efficiency and for operational efficiency. So just thrilled to have you on today, Zev. And
thank you.
Yeah. Well, is there anything else? I mean, Edwin gave a pretty deep dive into your background. Anything else you'd like to highlight before we dig into the content today?
I mean, I think we should get to what everybody's here for, the science.
All right. Excellent. So well, just to start and touch on what Edwin mentioned previously, we are going to be talking about both the solvent recovery application of membranes, which is applicable to ethanol, but also to heavy hydrocarbons like heptane, hexane, even potentially other hydrocarbons that you might want to use, and other alcohols as well. This is a very flexible platform. And this is the sort of starting point of our collaboration, but we're heading very quickly towards deployable DWAC solutions as well. In fact, I think we have our sort of Gen 1 solution locked in, so we'll be touching on that technology as well.
Yeah, it's those are definitely two of the primary functions. Something that wouldn't even be terrible to touch on at some point either would also be the use of membranes in solvent reproofing as well, which is something I've seen a lot of inquiries in, especially in the larger setups.
Absolutely. Yeah, that's something maybe we'll touch on that about sort of future trajectory for development at the end of the presentation. So we can start here. This is the core module as we view it. This is the X-spiral. I believe this is the X-spiral 8.
This is an X-spiral 8 model, yeah.
So solutions all the way from 30 GPM, am I right, in 30 GPM, 80 GPM, and then 400 GPM is sort of the range there?
Yeah, that's correct. Yeah, I quote some numbers in liters too. Those numbers are ratings for solvent recovery in typical use cases.
Great. So it's
In some
extremely
cases, you might
scalable.
even get higher results than that. And if you use a different solvent, you might get a completely different number. For hexane, the numbers are much higher.
Great. Yeah. So this gives folks, a little bit of a view into how compact these skids are. I should mention that SciPhy Systems and Molecular Forces are collaborating on an X-Spiral turnkey module that we're working on with a key engineering partner of ours. So this Molecular Forces X-Spiral skid, both all the way from the 2.5 to the X-Spiral 8, which we're viewing here, are available today for purchase. So if you have a solvent recovery demand in the ethanol or heavy hydrocarbon space, that's something we can deploy today with an 8 to 10 week lead time. DWAX also there is first gen DWAX capabilities available today as well. But in the future, by the end of the year, we will have a complete modular drop-in turnkey system all the way from dilute tincture to dry oil. So keep posted for that. We're going to be making some exciting announcements in the coming month or so.
Yeah, I'm very excited about that. And it was interesting when I first talked to you that we were kind of on parallel tracks with this development, because obviously one of the things I considered most heavily when I was designing this system, and as far as its physical layout, was that I wanted it to fit in the minimum floor space possible. That's why in this setup, a lot of other systems, they use double long housings to fit more than one membrane per housing. And I chose instead to lay them all out in a line with just one membrane per housing here, even though that's a little more expensive, just so I could get this more compact square setup. And simultaneously, while I was working on those kind of concerns, you were working on your distillation unit, which has its own space-saving arrangements that are pretty unheard of in the industry until now.
Absolutely, and another advantage there, which we're getting a little ahead of ourselves, but is that you can isolate each of those filters individually from the system to be able to change them out when you need to do that, rather than dealing with a more cumbersome two filters in one housing arrangement, which can be
Another great thing is that if you have a two membrane housing, usually you have to take the caps off of both ends to change the membranes, whereas with this kind of setup, you only have to take them out from the exposed side, so it's a lot more convenient.
Excellent. Well, let's dive into the sort of science behind the membranes here and the application for the hemp and cannabis space specifically. Get over here. So key to understand what we're talking about here, this is a cross-flow membrane. Can you tell us, sort of generally speaking, about what is a membrane even to start with? And then what is it about the cross-flow configuration that makes it ideal for this application?
Yeah, so generally I get a lot of inquiries from people who are just used to bag or cartridge style filtration, and they think this works like that. So they're used to filters accumulating material on them and needing to be replaced in the order of single uses and being treated as completely disposable. Conventional filtration is what we see on the left here. When mentioned in comparison to cross-flow, is usually called dead end, where you feed something perpendicular to the surface and push it through. And in that kind of filtration, which is exactly what you see in everything from a Buchner funnel to a cartridge to any kind of conventional filtration, they only have a certain holding capacity, because the more stuff is laid on top of them, the more clogged they become, and eventually they become totally impassable and useless. And that happens very rapidly because everything that goes into the filter just immediately obscures the surface. Now, what's interesting though is that the feed doesn't actually have to feed perpendicular to the surface. The only thing that there needs to be to filter is a pressure differential from the feed side to the other side of the filter. So tangential flow filtration uses really fast feed flow that is parallel with the surface. And the great thing about this is that the fast feed just continually washes away any stuff that's accumulating on the surface, as you can see here. And instead of just loading a big layer of sediment on top, you just have this nanometer thin gel layer that is determined by how fast the feed flow is, and it is actually a key parameter in determining the selectivity. So in a situation like this, instead of getting all your sediment on top of the filter, all the sediment comes out on the unfiltered side of the stream, and you end up kind of removing a slurry of all the particles that in a conventional filter might have accumulated on the surface.
Yeah, and just to give people a picture there of what that surface looks like, you know, what the actual membrane is itself, we're talking about either a polymer. In some cases, these are made out of mineral type bases, where you have, you know, nanoscale or micro scale pores in a surface, and they have, you know, different sort of geometry to the pores themselves, where they might have more tortuous paths or less tortuous paths, right? But you're essentially forcing with pressure, or very high pressures. I mean, we're talking about anywhere from 400 psi up to 1,000 psi here. You're forcing the smaller molecules through those pores while keeping the larger molecules that simply are too large to fit through the pores on the other side, and moving through that circulation path. Is that a fair summary?
Yeah, that's exactly how it works. And the great thing about this is because there's no sedimentation, these are consumable in the long run because of chemical effects that occur on the surface, but nothing accumulates on them. So you never have an issue of fouling caused by sediment unless you're, you know, running the system extremely slow, which is not the way an X spiral is intended to be run. And because of that, also, some people have had experience running these same membranes in dead end configuration in like a test cell provided by some vendors. And the results on those will be completely different, because when you run a membrane in dead end configuration, the selectivity of it is completely dictated by this sediment layer that forms immediately. So, you know, only the first second that you're running that, it might actually be representative of what it would look like in a tangential flow system.
Great. Well, you know, we've really touched on the how the system functions here in a tangential flow or cross flow filtration setup. I'd like to take actually a step back in the presentation and just highlight these long tubes at the top of this skid hold what is essentially a spiral wound membrane cartridge. And I'm not sure if you have a picture here of the sandwich configuration of those membranes, but you actually have a very high amount of membrane surface.
Yeah, I do actually. If you go to slide 3, I have a comparison of some different membrane geometries with the spiral wound type here on the right.
Yep. Yeah, so you can see on those larger spiral types how it really is a sheet or a sandwich sheet that is spiraled around. And can you tell us a little bit about like how the actual flow path works in these spiral wound cartridges?
Yeah, so I don't know if you have any ability to zoom in on this picture, but if you were to look at the spiral wound that's on the top left there, exactly that one that you're touching.
I don't think I can zoom in.
Oh, okay, well that's fine. I think we can see it all. You can see that there's the membrane sheets, which are the white parts, and then there is the black space between them. That's a spacer, and a spacer is basically like just a mesh of some polymer that is, you know, large sized. It doesn't do any filtration of any sort, but it separates these layers. So when you feed fluid, it goes in exactly like the way that we're looking at it right here, all the way down the tube through those spacer layers. And as it's flowing through the spacer layers, the pressure differential is causing it to permeate to the inside of those white membrane layers, which are actually hollow on the inside. They're like an envelope. And when stuff permeates to the inside of the spiral, inside of the membrane, it spirals into that central tube through these joiners that you can, I think, see 3 of them if you look really closely there. And then they enter the central tube. So the central tube collects everything that goes into the inside of the membrane layers, whereas everything that is not getting permeated just goes through the spacers all the way to the other end and comes out. And so you end up with 2 streams, one that's coming out of the tube in the middle and one that's coming out of just the bulk membrane around the tube.
Right, so you obviously are packing a lot of surface area into a relatively small package here. So
yeah, it's the highest surface area, and you can change the spacer too. You can see the spacer is biggest on the left one. That's why it's the one I pointed to. But if you look at the bottom right, some of these spiral bound membranes have very, very tiny spacers that you may not even be able to easily see, and those pack even more surface area. And the interesting thing, if you look at the trend here from a geometry that has very little surface area, like this tube and shell one on the left, when you're determining how much cross flow you need to keep the membrane surface clean and the gel layer thin, it's basically determined by how much dead space there is, because everything that's flowing in the middle of one of these holes is wasted and doesn't contact the surface. Only the stuff that's on the interface is actually doing any cleaning. So when you are running something like the one on the left, in order to keep it clean, you need a great abundance of cross flow to get the necessary velocity at the surface to scrub it clean. And the more surface area you can pack into a given size, the less cross flow you need. And that's why these spiral wounds are really ideal. They just get a lot more surface area per volume than any of these other types. And as a result, they're very easy to self-clean compared to these other types.
Right, so really highlighting that the primary cleaning cycle for these in-between cartridge replacements is just running fresh solvent through them. So it's really very simple ongoing cleaning, and that's your periods between cleaning might be fairly long, right? I mean,
to give a sense of perspective, if you look at a tubular membrane that takes up the same amount of space like would fill one of those housings, it may well be that the surface area you get in the tubular membrane could be 20 times less than what you might get with a good spiral wound membrane for the same space, and it would require many times the cross flow despite having such low surface area.
So how frequently do you need to do a clean flush out of these membranes approximately?
In my opinion, the cleaning flush has to be done every time that the system is turned off for any period of time. If you're running 24 hours a day, you may only want to turn it offline, when you hit the weekend, because what's happening the whole time it's running, the gel layer is continually getting scrubbed off by the cross flow. It's when the cross flow is off that any oils in the solvent have a chance to settle and become a really fixed gel layer that's harder to remove. So what you just want to make sure is that the membrane is never in a state where it's sitting with oil in it and letting oil settle into its pore structure. So I clean it out every time it's turned off, not so much to actually clean it, but to make sure that when it's turned off, it's sitting on fresh ethanol that can't contaminate it passively when it's, not being run.
So that's a key point. I mean, this is a fully continuous system meant to be run at industrial duty. So you're talking about, operating for full shifts or multiple days on end without a break in operation. So that's really a big advantage for, any industrial application. And if you don't have the capability in terms of staffing and that sort of thing to run a a full day multi-shift operation, then the shutdown procedure is really as simple as feeding fresh solvent into the system to completely discharge the loop, and then doing a simple shutdown procedure and leaving it with solvent in the filters to maintain that filter surface. So
yeah, correct. Yeah, the important thing is when you want it to be offline, you want it to be sitting in solvent so it doesn't dry out, and you want the solvent to be clean. The fouling potential, 99% of the fouling potential is when the system's turned off. As long as it's turned on, the cross-flow being provided these systems is well in excess of anything needed to keep it clean.
Great. Well, let's see here. What do we have next in the presentation? Yeah, let's talk about some advantages to membranes over conventional systems, because you have things like falling film evaporators that can do continuous solvent recovery.
Mm-hmm.
Why move to membranes?
Well, mainly, when you're running a falling film evaporator, there's kind of two key disadvantages compared to the membrane setups. The first is energy consumption. If you just look at the physics of it, when you're pumping, into a filtration setup, the amount of energy you're consuming is the volumetric flow times the pressure differential. It's pressure volume work. It is not that high, honestly, and I'll go into on another slide here. I have some actual math showing how it works, but when you're doing a falling film evaporation, every molecule has to go through a phase change into the vapor phase, and the energy consumption of that is just staggeringly high. So when you break down pressure volume work versus phase change, the energy use is 5%. And that's not even a theoretical number. That's like a realized number in development when you look at the energy use of a X spiral versus some competition here. It's actually even lower than 5%.
Right, and I got to highlight that we've sold the steam-driven falling film evaporators for a long time, and we're talking about potentially, depending on your scale, of course, but tens of thousands of dollars a month in larger scale facilities of energy cost savings here. So this is
easily. Yeah, I really break it down. You can be saving thousands of dollars a day with no exaggeration there, just from the energy savings alone. And then the other thing I'd like to touch on again is that this is a zero heat system. The only work is pressure volume. The only heat being generated is the slight inefficiencies of the pump, which is kept under control by a heat exchanger. And so the whole thing is done at room temperature, 20 Celsius. There's no heating. There's nothing that is going to be driving away volatiles, decarbing material, or causing any oxidation or degradation. So it is the gentlest way, despite the high pressures, to remove solvent. There's no heat involved, and it's great for anybody who's trying to produce high terpene or high in the acidic forms of the cannabinoids extract in a way that it's just really hard to keep under control when you're running all the solvent through heated recovery.
Right. Yeah, and this applies, of course, across multiple solvent systems, especially with some of those higher boiling point, lower vapor pressure, or across the whole spectrum of vapor pressure, really, solvents that you can use. Some of those heavier solvents require quite a higher temperature, and membranes offer a really great alternative to some of those solutions out there that we've started seeing people experiment with other types of solvents. If you have a high energy or high temperature demand on your solvent recovery stage, membranes offer really big advantages if you're aiming for a high quality extract output.
Yeah, and they don't have as high of a dependence on things like that either. Like generally speaking with a membrane, the throughput rates are much more dependent on the chemical species of what you're dealing with than anything related to their size. Methanol and ethanol permeate at extremely similar rates on these membranes. Pentane and heptane permeate at extremely similar rates to each other. You don't see the same kind of trends with increasing size having slower rates with these with these membranes. They're a lot more stable if you're experimenting with different solvents in that regard.
Great. Well, let's see. Now we've addressed this, the X spiral range a bit previously, but this is a key, visual demonstration of the different scales. You're looking at this innovative diagonal type orientation that really keeps the footprint small at the small 150 liter X spiral 2.5 scale. That makes ease of removal of the filters also quite simple. And then the horizontal orientation on the larger ones makes the removal and replacement of filter cartridges even easier with still a very compact footprint. So
yeah, everything about these systems was designed to take up not very much space. And I used to work in a lab that was only 400 square feet, where if I wanted a new piece of equipment, the first question wasn't even how much does it cost. The first question was like, can we physically find a place to put it? And with that kind of experience, I tried to make sure these could fit in any lab that wanted them, no matter how small. The smallest unit here is actually a little less than 3x4. So
yeah, so this really means
it's hard to find anything that could push a volume like 30 gallons an hour in that little space.
Right, and it means that even if you already have equipment in and you're just looking to expand capacity without having to move to a new facility, this is a great option for operators that have existing operations and are trying to really maximize the capacity of what they have already. So really great solution for that. And that's also our design philosophy on the secondary solvent recovery stage. I will say that essentially what we're looking at is an output of 2-to-1 solvent to oil generally,
yeah,
right? And so it does require a secondary stage of solvent recovery similar to an FFE. Some falling film evaporator companies have claimed that you do not need to recover any solvent after it comes out of the falling film evaporator in order to have a saleable product. We have yet to find a satisfied customer with that approach. All of our units include a secondary solvent recovery stage to get down to that true, 5,000 ppm or below saleable product level based on the regulatory limits of, the major player states in the United States. So that will come very soon. We're going to have a plug and play solution tying that in. Can't give away too many details on that now, but that is something to keep in mind for folks looking.
Yeah, it's a good point. Yeah, and in regards to people setting it up in their current setups, that it can often work really well in their favor because whatever they were using originally for their primary recovery can now become the secondary recovery. If they used to run everything through a 20-liter rotovap, you can keep that, and all you're doing is now you're applying a booster to get 10 times as much done.
Yep, absolutely. So here's we're talking about some hard pricing here. It's not something we do a lot in the field here, but today, motivated buyers, you can see the economic benefits of this technology. I mean, not only on operating expenditure, where you're going to have much lower energy costs and low costs of replacement on the filtration cartridges themselves. There are some other membrane companies out there, but we are working with Molecular Forces specifically because of the low operating expenditure, low cost of maintenance on filters. Yeah. But your startup costs, I mean, this is an extremely compelling offering on your initial purchase price. I mean,
yeah, even if you disregard all the arguments about energy savings, which you shouldn't because they're really important and we're going to drill hard into those later, but I try to make sure that not only on the overtime savings, but even on the upfront cost, it's competitive with any product on the market. And I don't mean to pick on True Steel for any reason. They were just the only people I could find that had all their prices publicly listed online.
Mm-hmm. Yep, and they are relatively representative of products in the field. But I will say is even we find these prices to be competitive even with the low cost, direct import vendors out there. I mean, this is cost per unit capacity that is across the board competitive.
Yeah, even with some of the import falling films that look like they have a really nice price once you get into developing the infrastructure for them. As far as the chilling and heating, they can get to be pretty significant, and it's not necessarily listed up front.
Now that's a key thing. These packages, they require electricity, and they require a very moderate amount of cooling capacity to keep the circulation loop cooled. From all you're fighting is the heat of the pump, essentially.
Yeah.
There's no active heating to cool. So you're talking about, again, a fraction, 10%, 5% of the cooling load needed for these systems. So your utilities costs, when you might have a steam boiler and a cooling tower to put in on the alternative, evaporative systems, this is, an extremely compelling offering. And our upcoming fully turnkey systems will include that chiller system and everything you need, including tankage to get up and operational once the skid lands. So that's again coming quite soon from us. We'll have the full turnkey solution out there. But as it is today, a simple chiller, mechanical chiller that doesn't have low temp requirements, just a run of the mill.
Yeah, it only needs to maintain the temperature you're trying to run at. So, 20 C, and a chiller running at that temperature tends to be at its highest efficiency anyway. So even one that is, might have not seemed adequate can do the work on this.
Great. Let's talk energy savings.
So here's the real benefits of the system. I takes a look at the energy. So first of all, up front, you can see only 30 amps to run this X-Spiral 8, and that is impossible to do with distillation, no matter how efficient of a setup it is. I picked what I consider to be, again, one that released its energy data online in an easy to find format. It's not even directly comparable because it's actually only does 300 gallons an hour instead of 400. But it's the closest one I could find. You can see the energy use is only 5.5% for my system. And if you're comparing apples to apples, it would actually be less than 5% because it's getting more work done with that energy. I picked a energy cost of 12 cents per kilowatt hour, which I found for California. I've had some inquiries from places like Colombia or Thailand where their energy costs are actually significantly higher than this, and that only increases the discrepancy here. But you'd be looking at a savings of $616 to operate it for 24 hours. And it would be, again, even more of a discrepancy if I was to look at that from a per unit volume processed perspective.
Right. So, look at that, multiply by 30 days in a month. And, you're, like I said, you're talking about almost $20,000 in savings just on the single month of operation. The system pays for itself extremely quickly as compared to other systems.
Yeah. If I were to pitch completely on this by itself, I would say, the system pays for itself in 1 year in terms of the energy savings. But of course, it's also cheaper up front. So, right. It already kind of paid for itself. But the ongoing expenses are just there's a titanic difference.
It really is. And another thing to keep in mind for operators in states that have incentive programs, and here in Oregon, we have the Energy Trust of Oregon. California also has tax rebate programs for sustainability. If you can prove an improvement over the existing standard of operation, for example, using this exact calculation we've done here, there are tax incentives for using a more energy efficient solution for an industrial process. So you're potentially not only going to save money on the upfront capital purchase and on your ongoing electrical demand, but there's also a potential to even save more money with additional tax incentives for states and countries that have energy savings, sustainability tax incentives. So
now, that's a really good point that I didn't even think to list on here. I'd be interested in going through that analysis at some point.
Yeah, absolutely. And it's I I think an angle that too few operators are taking and talking their states about those programs,
Yeah.
they really can make a big difference to the bottom line when bringing a new plant up to operation. Let's see here. Yeah, so let's talk, we haven't gone into too much depth on DWACs yet. Let's talk through DWACs as a process first before we get into these numbers.
Yeah.
So when, a lot of folks, they're using winterization, and that means that they're using a temperature swing in a solvent with oil in a solvent, and they're essentially chilling out the waxes and making them separate out from the solution at a set temperature. We see, commonly ethanol being used for this process. More recently, there's some methanol being used that has a higher temperature at which you can remove those waxes, although there are some toxicity issues with the use of that solvent that need to be very tightly considered. You really have to get it all out at the end of that process. So that's a deeper concern. But, what does this process look like for DWACs? How is it actually functioning to get?
Yeah, so the way this works, the function of the winterization step is practically identical to the function of the desolvation step. You take your feed solution, which is at room temperature. Looking at it, it will just look like all the fluid is in solution. But at a molecular level, there is a difference in size between the waxes and the THC or CBD that can be exploited here. And when you are doing this feed, the large molecules here you could take to demonstrate the waxes in this approach, and everything that goes through is the cannabinoids, the terpenes, and the solvent. The principle is exactly the same for desolvation, except in that case, what's getting blocked is the terpenes and the cannabinoids, and only the solvent is going through.
Right. So the basic way to imagine this is it's all about the size of the pores in the membrane, right? So it's a size exclusion process. So the waxes are larger typically than the cannabinoids that we're targeting. And so you're able to hold those waxes back using the membrane and push the cannabinoids through the membrane in the cross flow or tangential flow configuration with the solvent. So really, on the one hand, it is a much more efficient process because you don't have to have low temperatures. It's just based on pressure again. But on the other side of it, one could argue that there is it could be more efficient. It's a more effective exclusion of the waxes especially given a period of time. I mean, this is
there's certainly some factors. I mean, one of the things again is that usually winterization, it's a dead end style process. So you get the efficiency ends up being dictated kind of by fluid being entrained in this wax cake, which is something that will sort of happen in the cross-flow setup too, because the slurry that the waxes are being fed out in will have some solvent in it as well, but they stay in suspension and they don't form a huge brick, and at the very least, they can be washed with some additional solvent in a way that a cake just can't efficiently be done.
Right. So it's, you can see sort of scenario A, you're forming a big cake in this filter, be it a bag filter or a press of some kind, or even a lenticular filter cartridge, something like that, where you have a dead end and the wax cake just builds up on top of itself, and you have this sort of solid brick of wax that you're filling out. Buchner funnel is a very easy way to see this happening. Whereas in the tangential flow filtration, cross-flow filtration, you're actually essentially discharging a solution or a slurry of the wax out of the system continuously. And so it has some solvent still left in it, but as a benefit of that, you're able to continuously flow it out. There's never any time where you have to shut the system down to discharge the cake. And there's not really a necessity to have your operators come in contact with the solvent on an ongoing basis like you do on a typical filter change. I mean, this can be a fully—
Yeah, that's very true.
run.
That's very true. And people often ask me, because, you know, every kind of filtration, whether it's lenticular, whether it's a filter press, all of these are ultimately dead-end filtration techniques. And so I often get asked questions coming from kind of that perspective, like, do they foul faster if there's more waxes in the solution? And how much wax can they hold? You know, these questions, though, are not really relevant to cross-flow filtration. And what dictates the speed of fouling in cross-flow filtration is, again, it's not how much contaminants are in the solution. The fouling potential really happens anytime that things are allowed to set from lack of cross-flow.
Right, so you can have these waxes fairly, fairly concentrated. What sort of target concentrations of the wax in solvent are you typically discharging at?
Well, again, it's going to end up being much like the solvent recovery step, about a 2-to-1 of solvent to wax.
Which that's great results there. I mean, you might say that, you know, compared to one of these dead end filters, that's a relatively high proportion. I would say that it's completely dependent on how effective those dead end filters are at preventing solvent buildup above the cake. Oftentimes with something like a bag filter, you have essentially a puddle of solvent on top.
Yeah, sometimes you got to even like pour them out and like rerun the stuff that didn't make it through, if it's a sort of filter that has a lot of holdup volume.
Right. So
and so you can tell the amount of solvent, again, the amount of solvent that is getting lost, so to speak, is thus dependent on the amount of wax. So for a low wax extract, getting that 2-to-1 ratio isn't going to be a whole lot of overall volume. And so when you're running like even a warm methanol extract, which has waxes but not a hideous amount, you'll get almost all of the fluid through with no need for any washing. Whereas if you try to do something like a CO2 extract, there's a lot more waxes. There will be more solvent in the waxes. And there will be, if you're interested in trying to preserve all that solvent, there will be more needs to do some kind of washing procedure.
Right, and we can also set up our clients as it is today with a solution to just simply recover the solvent out of those waxes directly.
Yeah,
if that's
true.
something that they would like. That's something we can offer very readily. And in the future, this will be a little bit further out than our complete turnkey solvent recovery membrane, but SciPhy Systems is also planning on a turnkey de-wax membrane skid as well that'll include some of these options we're talking about to effectively separate that wax out from the solvent residual. But overall, just having a continuous flow de-wax system, you don't have to wait 24 hours for it to freeze. You don't have to wait for any sort of temperature swing. It's not batch in nature. It really, you flow it in from a tank, flow it out on a continuous basis. This is just the sort of ease of operation that you simply don't get with any other de-wax operation that's out there.
Yeah, and one thing I'd like to touch on just a tiny bit is even if you are actually doing a process like sterile filtration that has permanent residues that are solids, undissolved solids, TFF can be used even in that scenario. There's actually cross-flow microfilters at like 0.2 micron, 0.1 micron that can very rapidly filter a large volume of solution of all particulate. And you don't even need a fancy skid to be running that, because the pressure that it operates at is only, the 50 PSI or so that it would have operated at in dead end configuration.
Yeah, I mean, that's great to note. It's, this platform, this X-Spiral platform is really highly adaptable. So if we have users that have unique challenges that they're looking to solve, that they're tired of using dead end filters where they have a lot of manual interaction and labor cost going into operating that, Molecular Forces SciPhy Systems were mutually supporting each other in always experimenting with new solutions. So if you have a challenge, you want to go continuous, you want to intensify your process, reduce your labor load, this is what we're here for. We're looking for inquiries to try and address specific client needs. So let's get back to the winterization energy savings. Now, obviously, with the traditional winterization, especially using ethanol or some of these other solvents where you have to go quite deep into the low temperatures, those chillers are eating up some energy. Let's talk comparison points here.
Yeah, this again, compared to the solvent recovery, here we're looking at two processes that are just very different in the way they're executed. You know, a solvent recovery membrane is basically a drop-in replacement for a falling film, whereas this is a little more, it requires a little more consideration to think about how they compare apples to apples. But so the membrane's simple enough. It operates the same way as the solvent recovery did. The energy consumption is the same, whether you're running it in winterization or solvent recovery, because again, the skid is exactly the same. The pumps are the same. The only thing that changes is you just take out one type of membrane and you're instead running a different one. Here in the winterization, I attempted to look at a process where like you cooled a jacketed tank or you cooled through a heat exchanger. And I found the biggest cooling system that matched up with the throughput of winterization. And you can see I found one that can cool down to -60 at that 1,500 liter per hour rate. A lot of people swear they got to winterize at -80. I couldn't even find a chiller that could keep up with this kind of rate at -80. You know, I'm sure that the energy considerations, if I was looking at that, would have been even more stark, but if the data isn't publicly out there, I can't really list it. This system, we'll say you're doing a -60 winterization. It can cool sufficiently in that area. It takes about $285 per day in savings, with some considerations because this system actually is a water-cooled chiller and it requires its own chiller to chill that chiller. So you're obviously magnifying the space requirements and energy requirements even more when you look into that factor, which I didn't get into quantifying, but we could expect a reasonable increase.
Right. I mean, this is, you know, and the thing that I would say is that this is actually quite a generous comparison, because you're talking about cooling 1,500 liters per hour to -60C. But the flip side of that is that most winterization operations out there that we see in the field, they are keeping that liquid cooled for several hours at a time. So that even means that you're cutting this this rate effectively in half, or by by 2/3. You're reducing the rate by 2/3 if you're, say, 3 hours per winterization operation. Some operators even go as far as 24 hours.
Yeah, that's a really good point. You know, and if I had taken that category, I could have said that this would take 24 times the power savings listed here, in which case, yeah, you're right. That obviously, you know, destroys the case that this will be an economical comparison and makes it even more of a huge difference than the evaporation case. But
right.
I'm trying to list numbers that, you know, are hopefully favorable to the competition. I'm not trying to dump on anybody.
Exactly. I mean, that's the key thing to emphasize here is this is extremely conservative. I mean, base it on your own experience out there in the field if you're already operating one of these winterization systems. If you have experience with a specific SOP, use your own apples to apples comparison. Basically, per hour that you're running your DWACS at that low temperature, you can.
Well, I guess what I was really trying to think of here was like a case of like a cold solvent extraction, where you pre-chill the tank of fluid and then you just use that for extraction, and then you don't actually have a proper winterization step with like a lag time.
Right. Right, and I from our experience, that when you're using ethanol, at least, that doesn't effectively prevent waxes. I mean, it's definitely superior to a hot solution, but it isn't like it is as good as if you had done a low temperature precipitation type winterization process. Now, this is something to emphasize here. When we're looking at this membrane, would you say that essentially you're able to get equivalent results in terms of wax load in the extract using warm solvent as you would getting an extract with cold solvent? Is that?
Yeah, I would say that the wax removal is very comparable between the case of using the membrane versus using a -60 ethanol extraction like run here. Obviously, some people, they go through very intensive de-waxing procedures. They'll dissolve in like methanol with water added, cool the whole thing to -80. Some people take very extreme approaches to try and remove, every possible molecule. This is, but I'm trying to compare what I thought was a more apples to apples case, which was the typical cold extractor.
Mm-hmm. Right.
Like you said, there's such variance in the SOPs for the batch style of winterization that it would really be hard to come up with a number to put here for that method.
Right.
Except that, like you said, in all cases, it's less favorable from an energy perspective.
So let's talk about the purity of output in the testing for this with the existing membranes, which again, new generations of membranes coming out all the time, increasing throughput capacity, increasing the efficiency of the process. But with your existing tests right now, what sort of potency numbers are you seeing output from input
for de-waxed crude that has been through the process as it's coming out in the form of crude? I'm looking at numbers in the 70s as being most typical.
Okay, and that's starting in what sort of starting concentration?
Well, generally speaking, when I've been running these tests, it's been extract direct from the extraction machine through these membranes, as opposed to a case of redissolving. But if I was to look at the average room temperature ethanol extract that I've seen, a number like 50 is more typical.
Right. So this is very comparable again to what you would see with a low temperature winterization approach. I mean, that sort of swing between 50 up to 70. Again, you're just
another really cool thing I would like to bring up is that none of those winterization processes that involve just temperature swings that were applied to a warm extract remove sugars from solution, which this actually does. It clears out substantially all the starches and sugars that cause no end of grievances to people who run warm ethanol on a hot solvent recovery.
Right, and that's down to the very small size of sugars, which I assume something like glucose might pass through, or is it really able to eliminate pretty much all the sugars?
Well, that's hard. That test was run in a qualitative way. I actually did in the past isolate those sugars and send them to an environmental testing lab. And what I found was that what people are calling sugars, only 10% of those are actually simple sugars that can be identified from a panel, things like glucose, fructose, etc. The great bulk of them are polymeric sugars or proteins. So those are the ones that are eliminated. Yeah, you could expect perhaps 10% of them that are actually monosaccharides to make it through. But despite the fact that people are calling them sugars, the bulk of the solution really isn't.
Right. It's really those carbohydrates of various types.
Right. So you got like the broken down pieces of cellulose and starch and gums, and then also collected in that is not just sugar, even though that's what people are calling it, but also another good 10% of that is proteins, and another amount of that is DNA. This is based on the testing results that I got done from Pixis Labs about 2 years ago.
And so a big thing to emphasize there is that for those folks that are going to distillate, these sugars are often one of the biggest culprits for fouling in the white film distillation process. You see sometimes people are getting black flakes of sort of carbonized material getting into their distillate, or just over time building up a very tough sort of dark coating on the surface of your white film. that's likely coming from these carbohydrates and some other additional compounds. But using this DWAX membrane solution, you're getting that carbohydrate reduction as well. So you're potentially improving your maintenance cycle on the downstream equipment as well.
Yeah, and for people who are big fans of using absorbents in their process, putting this upstream of that is a great way to eliminate a lot of the gums and polar contaminants that tend to block the active sites and make you need to use the media a lot more than you should.
Mm-hmm. Right, so again, reducing that downstream operating cost of replacement materials. So we're getting close here to the time when we are going to start taking questions from the field. So if you have any questions, I'd encourage you, please put that into the chat box or the Q&A feature on Zoom, and we'll be getting to those very shortly. Let's see, do we have any additional slides? Yes, let's talk about scale.
Yeah.
We're talking right now about 400 GPM, but that's not the limit, right?
Well, we were talking about 400 gallons per hour.
Sorry.
Now, if you want to have this discussion, yes, we'd be looking at more like 400 gallons per minute. Obviously, I didn't make this skid. It's not even a skid that I would make because the housings are plastic. This is from a desalination facility in Dubai, I believe. But these sort of setups, they use what's called a cascading or multi-stage reverse osmosis setup, where instead of doing any kind of recirculation either externally or internally, they start with many parallel streams of fluid. So you say you start running, you split your feed into 4 streams, and you run them through as many membranes as you possibly can until the point where the crossflow has dipped below where it should be. And that could be, 8 membranes would be a typical number. And then because the crossflow has been brought down, say 50%, you then unite the streams into a new stream that has merged the two and now has double the flow. And you send that again through another round of 8 membranes. So we've gone from 4 streams to 2. And at the end of that, you can merge those again to another stream. That would be called a 3-stage setup. And with a setup like that, with so many membranes, you can get 90% solvent recovery just in a single pass through this setup with no recirculation whatsoever. And when you start running it in that mode, the energy requirements are even lower than what I was depicting, even compared to the X spiral type of configuration. You'd be looking at only 50% the energy of that.
Mm-hmm. Right, so if you're going big scale, membranes are the solution for you. I mean, it's proven in other industries. We're talking here about desalination, reverse osmosis, which is a very comparable process, but it's also used in petrochemical industry and in numerous other industries where this has been scaled up to very large throughput volumes. So,
yeah, another really good thing I would like to bring up, which I know you are very interested in, is GMP and food safety regulations as well, is that these membranes are highly used in the dairy industry. And as a result, membranes have already been specifically made for sanitary clean in place requirements. They've been designed specifically to not have any dead space, to just be cleanable through flushing alone, and have already been implemented in things like cheese making.
And that was a big part of what we like about your facility, or not your facility, your design, I should say, is that it is full drain. So again, as part of that clean in place solution, it makes it quite straightforward to fully clean this, both as far as clean in place, circulation type cleaning, but if you have to ever do a shutdown procedure and you're changing out your filters and you want to do a complete drain and deep clean of the total system, this has a full drain capability that allows you to avoid any dead space and really do an SOP that's going to be FDA compatible. So really appreciate that design feature.
Yeah, and another point I'd just like to make again is when you have industrial style membranes, like ones that by and large have been used by every other vendor out there, have special geometries that focus all the feed flow into the tube, but they also in return create dead spaces that don't meet clean in placeability. When I designed these systems, I made sure that my crossflow was designed to hit the highest possible crossflow demanded by sanitary style membranes. Many people have been using the industrial style membranes that are not sanitary to compensate for the lack of crossflow their systems can deliver. I'm not sure there's any systems out there besides mine that were designed to meet the requirements of sanitary membranes, which can be up to twice as high even for geometries that are the same in all other aspects.
Excellent. Well, I do see a question coming in. I want to just take one moment before we address that question, and please, anyone else that has questions, please post them in Q&A or in the chat. But as it stands, do you have an estimated, cost of replacement of the filters on an annual basis? Let's just talk about that larger end of the scale, 400
yeah, sure.
GPH, gallons per hour. Sorry for the GPM. But yeah, 400 gallons per hour throughput. Like, what's a typical yearly filter replacement cost?
Yeah, so to fully stock an X-Spiral 8 requires 4 membranes. I have a few different membranes on offer, and just to kind of give the pessimistic case, I'll go with the most expensive ones that are used for ethanol. Those are 2,200 per membrane, so a full restocking of the system would be 8,800, and these membranes run about 3 months before they foul. So you'd be changing it 4 times a year. That's $35,000 on annual replacement fees for the most expensive membrane. If any people have membrane experience from other vendors, you might notice that that's the price some other people have been charging for one membrane, not 4 sets of 4.
Right, and again, that's on the pessimistic side. There are potentially more cost-effective solutions that might meet your client-specific requirements. So please contact us.
Yeah.
But just to go back to the numbers we were looking at previously, we're talking about energy savings as compared to an evaporative system over 2 months that cover the entire annual replacement cost of filters, which is its primary operating expenditure. So this is, again, the cost savings on energy more than compensate for the need to replace the filters.
Yeah.
And you have the ability to, as X-Spiral, as Molecular Forces identifies better membranes that might have higher throughput capacities or other better features, you have the ability to swap those out when those become available. So keep that in mind.
Yeah, I'd like to bring that up too, again, because ongoing research is constantly being done, and there are well over 15 vendors that I'm in dialogue with, and that are specifically formulating and sending me test elements for their own offerings in this category. The expectation, unlike pretty much any other piece of equipment out there, is that the throughput of this over time will actually increase from when you buy it, because changing the elements alone will lead to a boost in productivity. And I don't think there's too many things out there that you could say that about.
No, it really is an extremely interesting product sector that has numerous advantages. I mean, it's really advantages on all fronts from what we've seen, especially in the solvent recovery category and moving into the DWAX category as a replacement for winterization, really strong. So I see some questions out there. Let's go with Dylan Boskia's question initially. Is it true that one still requires an evaporative process to remove residual solvent after the membrane-based solvent recovery? What ratio or percentage of alcohol must be evaporated after this process?
Yeah, so we did address that actually, but I'll bring that back. I'll bring it up one more time. So the solvent that is the retentate stream in the when you're recovering solvent is about 3 parts oil to 7 parts ethanol. And so if you want to know the amount of solvent that is being recovered, you need to know what you're starting with, and based on that target number for the output, the mathematics dictates what the proportion of the solvent that's recovered is. So to do an easy case, if you started with extraction tincture that had come out, and if you tested that tincture and right out of the extractor it's 3% oil in ethanol, then you would expect to bring it from 3 to 30, and that is equivalent to a 90% ethanol reduction because it was a 10-fold concentration. And no matter what you start with, you're going to peter out at around that 3 to 7 ratio. So, you can infer the efficiency of the process based on the starting material and that end material.
Right, and keep in mind, SciPhy Systems, by the end of the year, we're going to have a fully integrated system that includes that last stage, solvent recovery. We can speak to clients interested in early models that include that technology. It is something that we're not yet announcing, but will be announcing very shortly. But this is, again, a truly continuous solvent recovery solution to get down from that 30% oil and 70% alcohol down to trace saleable oil. So that's something that, stay posted for those turnkey skids that we are developing together. And in the meantime, if you have some existing solvent recovery capabilities, capacity for something like perhaps rotary evaporators essentially any kind of batch solvent recovery that you might use, right? That could be appropriate. We typically in the past have done pot stills, like large agitated reactors with pulled under vacuum with a condenser. That's something that we have deployed previously for this type of larger process that you might not want to use some of your more lab scale products for. But there's a variety of ways to approach this, but it is that 70% alcohol.
Yeah, and you're working, of course, your evaporators that you're about to deploy, they're designed to do what those other falling films were failing to do, which is to continuously get it to actual dryness.
Right, exactly. And we know that that is a big concern for operators that are going downstream to post-processing, and should be a concern to operators trying to sell acid form crude oil to end users. I mean, or to end product manufacturers. I mean, end product manufacturers do not want trace alcohols, trace solvent in the product when you send it to them, unless they specifically request a dilution. So that's been a real problem for the industry. We think that you should be able to onboard your system, get down to, at least below 5,000 ppm or better. And that's something that we are deploying very, very soon. So let's see, Brittany Spencer, what is the downtime with no flow before you must do a flush? Can it sit for 20 to 45 minutes between runs without a flush?
That's a really good question. And yeah, the answer is yes, it can. And let me explain. When I talk about degradation on account of not having washed it and letting it sit on dirty solvent, that's a gradual process. Even if you were to leave it overnight, it's not like you'll get up in the morning and your membranes have like fallen apart and failed completely. It would more be a matter of like, if that's a bad habit that you are continually doing and you're never cleaning it, you might see the membranes fail in 1 month instead of 3. So there's no damage that you're going to incur, just from letting it sit for 20 minutes, or even letting it sit overnight once. It's just an SOP that you need to enforce, through your whole practice to ensure maximum lifespan of these things. Fouling is not something that causes sudden critical failure. It's a gradual issue.
Right.
So I would say you're totally safe to leave it sit for 20 minutes, just if you can avoid it, don't do it.
Right. And as far as the turnkey solutions, those are going to have essentially onboard valving and appropriate piping and controls to essentially quickly and immediately do the flush cycle. So that's something to look out for the future all-in-one skid that'll be coming out shortly. I see an anonymous attendee saying, when it's done, the stream of ethanol contains fats and sugars, where does it go and how is that solvent recovered? So So this is a question that in the short term, the user would either supply tankage, or we at SciPhy Systems could supply you tankage to receive that retentate stream from the DWAX solution. And that is going to be output again. I believe we've said that also is at about a 30% load of dissolved compounds to 70% solvent. Is that right?
Yeah, that's going to pretty much be the limit of solute concentration, pretty much irrespective of what the solute actually is.
Okay, so that is going to come out, and we could spec you, for example, a batch still to be able to evaporate the solvent out of that oil. There could be some alternative solutions to filtering out the oil from the wax. But that's something that will be addressed on board the turnkey solutions that are going to be coming out in 2021. However, if you purchase one of these right now, probably some sort of batch evaporation solution is what you would go with. And because, well, we would work with you specifically depending on your demands. If you want to use those waxes for a product downstream, have it a value-added byproduct stream, then we would take a different approach than if you're treating it as essentially a waste stream that you just want to get your ethanol out.
Yeah, that's exactly true. I mean, that question is in large part a question of what you want to do. Obviously, evaporation would be how you could most easily recover that solvent. But you know, whether you want to try and do anything productive with it first is a very good question.
So I see Brittany has come in with another follow-up question. Are there adjustable flow rates? Does expect the extraction? I'm not sure about the question about extraction, but as far as adjustable flow rates, let's address that. If a client has less than, say, the specified volume coming out of their upstream processes per hour, that can be accommodated with the flow rates into the feed of the system. Is that right?
Okay. Yeah, that's a if that's how that question is to be interpreted, you know, I would say that, you know, generally you're not going to just take fluid from your extraction and pump it directly into the skid. You're going to utilize some kind of buffer tank in the middle. And so there really shouldn't be any issue with outpacing it. There's different things you can do to actually, if you want to slow it down, you can slow it down most easily by reducing the pressure that the system's being run at.
Yeah, so that essentially would mean you're permeating less solvent per hour or per minute, and so you're able to feed less solution into it. And that, I think, is important mostly for clients that may have an output of only, say, 150 or let's call it, say, 300 gallons an hour coming out of extraction, right? But they want to have it be a continuous solution where they have an operator not having to adjust it on the fly or shut down the system periodically or something like that. You would do that by operating at a lower pressure to achieve a lower permeation rate, less ethanol coming out of the system per minute or per hour, in order to reach an adjusted steady state to have a lower input feed rate. Is that?
Yeah, and another thing you can do also is if you're not using the full capacity of the machine, you can actually try and push the ratio of concentration higher. I say 30% is the limit because the machine becomes pretty slow at that point. But if you have plenty of spare time, you can drive it up to 40 or 50.
Great. So yeah, if you have less than the target spec of of capacity input, perhaps you have a less evaporation work on the residue side, which that's just a great benefit.
And but I believe that, I'm not sure if that was really, because I when I read this question, I interpreted it as referring to the cross flow rate of the machine, which, yes, it is adjustable. It just to use the XBarrel 8 as an example, the maximum cross flow rate is 100 GPM, and the turn down ratio is 1 to 10, I believe. So you can get it down to 10 GPM minimum. And that's all controlled by a variable frequency drive that's totally incorporated into the controls. It's a free floating parameter, and how it would affect generally speaking, it doesn't have an effect that I would consider overwhelmingly positive to try and slow the crossflow down. It can, in the short term, make the rejection more complete. Like if you get a tiny amount of color through, running the crossflow slower will increase the size of the gel layer and can actually start blocking some stuff that was making it through before. But at the cost that when you're allowing the gel layer purposely to form to try and do some blockage, you're gonna reduce the lifespan of those membranes. So I think it makes more sense to get more, if you're having that problem, get more selective membranes, boost the pressure, keep the crossflow strong. That's how you're going to achieve the most long-term use out of these membranes.
Now here is a question that is extremely important to address, and that is the machine controlled with manual inputs or an electronic interface? What's the user interface look like?
So the machine, so I make all three models with completely automated electric interfaces. And for the very smallest of the units, I offer a pneumatic version because the energy consumption of that skid is so small that it can actually be run off of pumps driven by compressed air as like a budget option for very small labs. For instance, in the legal cannabis field, as opposed to hemp, might have more demand for a small unit. That one is manual, but they all come in electrical versions, and the larger two units only come in the electrical version.
And that's operated via touchscreen HMI, is that right?
Yeah, they're operated via touchscreen HMI, which is C1D1 compliant in answer to this question that just came in. Yeah, it was designed for C1D1, and obviously by default also works in C1D2 for that reason.
What about NRTL certifications? Are you using UL components or other,
Yep, these are UL components, and they're built at a UL shop that has its own certifications.
Great. So, really ready to go into any sort of regulatory environment. C1D1 compatible, which is great because you could go into C1D1 facility or C1D2 facility equally well. So very adaptable solution. Let's see. I see a question about remediating color. Yeah, what about color remediation?
The DWAX membranes do remediate color to a certain extent. Generally, the color that makes it through is chlorophyll. Chlorophyll has the hardest time getting rejected by a membrane because its structure is very linear. It's like a pretty long string if you look at the molecule. So even though its molecular weight is pretty high, it can kind of make it through the pores if it hits them in a perpendicular, like axial way. And as a result, chlorophyll tends to make it through membranes that you would think it wouldn't. Other molecules, like some of the red colors caused by carotenoids, those get rejected much better. So generally what I see with these systems is that they reject most of the red colors and let substantial amounts of chlorophyll through. If you use them in combination with carbon, I would say the overall effect of color remediation is quite good.
Right, and so we do recommend a pre-filtration stage for this membrane, just mainly to remove fines, because you don't want any particulate, cellulose-containing fines to get into the filters. They can be damaged by, essentially getting surface scratches due to large particulate. So as part of that pre-filtration, including either a carbon or another sort of media-based filtration to remove the chlorophyll specifically.
But I would say that certainly you want to filter all the fines up front, but it could actually be more favorable to put the carbon after the first dewaxing membrane, again, because having removed the gums and sugars with that step, you won't have stuff fouling the carbon as much, and it'll last longer if you put it afterwards.
Absolutely. So, again, as it is today, we can work on a custom basis to meet any specific client specification. There's advantages and disadvantages to multi-filtration stages. You have to be concerned, of course, about having pumps to provide the appropriate pressure. So if it depends on if budget is your biggest emphasis, or efficiency of operation, reducing labor cost, reducing cost of filtration media is your highest priority. We can address, any one of those specific client priorities today. So please contact SciPhy Systems, and we will, walk you through this process of getting you outfitted, not only with the membrane, but also with all the accessory components that you'll need as well.
Yeah.
Let's see. Is there
another question here?
Yeah.
Is there a secondary or critical moment filtration if a failure of the membrane occurs? I'm a little confused about this question. I think what you're asking is what causes critical failure of a membrane, and the main thing that would cause critical failure of the membrane is allowing solids, undissolved solids into the system. So if you don't have any kind of pre-filtration and you're just allowing like keef to go in, that will scratch the membrane surface and it will cause some pretty rapid loss of selectivity. That's the number one way to kill a membrane. That is the number one way to kill a membrane. It's much more damaging than the concerns about letting it sit on a dirty fluid. But undissolved solids, clay, keef, those things are, need to be handled with very good upfront filtration.
Right, and as far as concerns about like a catastrophic failure of the membrane, where maybe particulate from the membrane itself gets into the stream or something like that, we would work with our clients to specify a downstream filter that would be able to catch any of that. But
if a membrane actually breaks, which is not, something I've experienced. If I suppose on some very cheap membranes, you could potentially have the permeate tube crack or something if it was improperly handled or got, smacked into something. The more expensive membranes have stainless tubes. If that were to happen in a run, what would happen is the pressure differential would immediately become zero, and the system is designed to turn off if that happens.
Right. Yeah, and that is, we always would recommend a downstream buffer tankage before going into any other processes. And typically, if a failure was detected, you'd want it to be set up so that downstream tankage holds and doesn't discharge to the downstream process until that failure has been analyzed. So that would be another part of the sort of fail-safe procedures. And it is dependent, of course, on what your GMPs you're targeting, or what, how rigorous you need that downstream protection to be. We would address that specifically with each client as far as that downstream protection. Are cut sheets available? Absolutely. Email, please email either Brandon C at sciphysystems.com, or you can email Emmett M at sciphysystems.com to get additional follow-up documentation. Zev is also available.
Yeah, I'm at info@molecularforcesllc.com.
Yep. So
and feel free to reach out to me on any extended questions you have.
Right. And we are getting towards the end of the show here. Let me make sure that.
So we are.
I should have stopped screen previously. Apologize.
We just got a good question.
Yeah.
About the thing that I was planning on talking about, but I forgot to. Where did that go? Somebody just asked about.
It's in the chat. It's in the chat. Methanol water separation, or alcohol water in general. What about reproofing alcohols from water content?
Yeah, so that is indeed possible, and it requires. It isn't done in the exact same way as the X spiral. If you were to order a unit for reproofing, it would be different from the 3 I showed here. The way that works is you have these special membranes that are permeable only to water and only in the gas phase. They're actually the exact same material used to make molecular sieves. And what you do is you superheat your whole solution of water and ethanol, and you run it through this membrane, and the permeation of the membrane is under vacuum. And so when the superheated solution hits this membrane, immediately the only thing that can permeate is gas phase water. So the only thing that feels the relaxed pressure is the water. So you boil off all the water and you don't boil off any of the ethanol. So the amount of energy used to take the phase change is much reduced to only be a portion of the solution instead of all of it. And also because this is absolutely impermeable to ethanol and very permeable to water, it doesn't experience any kind of azeotrope. It can be brought up to arbitrary concentrations of ethanol.
Right, so that's the new cutting edge reproofing solution being worked on by Molecular Forces. I believe there are existing versions of that platform that could be made available quickly as well.
Yeah, this is not, that's not an approach I invented. It's actually widely used in the biofuel industry. It's called the pervaporation process.
Great, well, I think we are really at a great moment to break. I want to thank everyone. If you have one last question, we might be able to address one last question. But unless we see that come through, I just want to take the moment to thank everybody for attending today. Thank you, Zev, for coming on and for working with us. We're very excited about these X-spiral membranes and the total platform that we're working on together. I hope that this has been very enlightening to our audience and that you're feeling motivated to switch over to a membrane-based solution for your solvent recovery needs, as well as DWACs and other needs that you might have that can be addressed on a continuous basis by membranes. Please do reach out to us. You can find us at sciphysystems.com, SCIPHY systems.com, and molecularforcesllc.com. We are here to serve you with any of your needs. Also, SciPhy Systems supplies the hemp and cannabis industry with solutions all the way from extraction through finished crystallization, if you'd like to go to isolate, distillation, the complete product set. We are launching brand new product lines throughout the winter going into 2021. So please stay posted to our Instagram, Facebook, LinkedIn, all the social media, as well as our websites. I think the same might go for Molecular Forces as well.
Yeah, I do, except my Instagram is not under the name Molecular Forces. It's actually at Magister Chemist.
Okay.
And I got one quick question for you, Emmett.
Sure.
I have a question. These, this is being recorded and it will be hosted as a video on YouTube or some other platform, right?
That's right. Yep. This will be going up onto YouTube, and there is a video section on our website, sciphysystems.com. We can also provide you a link, Zev, so that you can put that onto your website if you would like. And we will also tag you in one of our upcoming posts when we post this video up to YouTube.
Excellent.
Great. Well, thank you all so much for attending today. We are really glad to be presenting. Please do let everyone know that this new technology is available, and the price efficiencies are great, not only on the operating costs, but also on the upfront. This is extremely competitive with anything in the market. So we are glad to be helping bring it to the market. Thank you, everyone, again for joining us. Zev, thank you. And we look forward to speaking with you all again. Our next episode will be announced very shortly. We're going to be talking about new products, offerings, what's coming down the pipeline for SciPhy Systems, and we're going to be speaking with some actual SciPhy Systems staff members as well. So stay posted for that announcement. Find us at SciPhy Systems, SCIPHY Systems, on Instagram and other platforms. I hope you all have a great rest of your week. Thanks again, Zev.
Thank you.